Hello friends, my name is Chinmay Deshpande. In this video lecture, we are going to discuss about a topic from power system stability, and the topic is methods to improve steady state stability and transient stability. Let's first discuss about methods to improve steady state stability. Now we know that what is the formula or relation between P and delta. P will be equal to what? It is E into V upon X into sine delta. So first method is nothing but reduction in the transfer reactance. Lesser the value of the X, what will happen? More will be the value of P, that is power transfer capability. So a power system that has a lower value of transfer reactance can have a better steady state stability limit, which can be achieved either by using two parallel lines, because we know that when we have two parallel lines, when we have two reactances, let's say, which are connected in the parallel, then the effective reactance of that line will be lesser compared to that of individual one. Second one is nothing but use of series capacitor, that we will discuss when we start with the next topic. Third one, if the power has to be transferred through a long distance transmission lines, the use of parallel lines reduces a transfer reactance as well as it improves the voltage regulation. So therefore, here if you see, when we use a parallel line, effective reactance will be reduced. Not only it reduces the effective reactance, but also it improves the voltage regulation. And similarly, the series capacitor sometimes will be employed in the lines in order to get these same feature. The second method is nothing but increased in the magnitude of E and V. You can increase this E or you can increase this V. So higher and the fast field excitation system will enhance steady state power limit. Let's discuss factors affecting transient stability. First is post-disturbance reactance. This post-disturbance reactance is nothing but what? It will be your X3, which is represented as X3. So, if the post-disturbance reactance obtained is weaker, the post-fault Pmax will be a lower, and hence the system may undergo an unstable state. Second point, fault clearance time. The more will be the fault, or the longer the fault is applied, the longer the rotor will be accelerated and more kinetic energy will be gained. The more energy that has gained during the acceleration, the more difficult it is to dissipate it during deceleration. So the fault clearing time should be lesser as much as possible. Third one is inertia of the generator. We know that more the inertia, then slower will be the rate of change of angle. And if the rate of change of angle is slower, then we can say that the kinetic energy which is gained during the fault, it will also less. Third point, internal voltage of the generator and infinite bus voltage. Here, the internal voltage of the generator, generally we represent it as a capital E. Infinite bus voltage is V equal to 1 at an angle 0, or we can represent it as 1 per unit. So lower the voltages, lower we will get the Pmax value. Loading of the generator prior to the disturbances. More will be the loading, the closer the unit will be to the Pmax, that is maximum value of power, which means that during acceleration it is more likely to be unstable. And last point is internal reactance of the generator. The lesser will be the reactance, the higher will be the peak power, and lower will be the initial angle. Now let's discuss about methods to improve transient stability. We know what is a swing equation. It is m d square delta upon dt square equal to Pa. Pa is the accelerating power, which is equal to Pm minus Pe. This is nothing but your equation of Pe. And how we can write Pe? Pe equal to Pmax sine delta, where we know that what is the value of Pmax? Pmax equal to what? It is Ev upon x. So improving the transient stability means reducing the rotor acceleration. So lesser the rotor acceleration, more will be the stable system. So what are the methods of improving transient stability? First is design the alternator with a high capacity or with high rating with a large moment of inertia. Because we know that more the moment of the inertia, lesser will be the acceleration and more prone the system to be stable. A heavy machine has a greater inertia and it is more stable as compared to that of light machine. Second one is nothing but reduction in the transfer reactance with the help of a series capacitor. Now we know that the amplitude of the power angle curve is inversely proportional to the transfer reactance. So I can write P equal to EV by X. So P is inversely proportional to X. So if we can insert the capacitance in series with the link line when the fault is clear by opening the circuit breaker, then the amplitude of the post-fault power angle curve will be increased. Let's discuss this in the next slide. By inserting the capacitance will reduce the overall post-fault transfer reactance, because we know that when we are inserting capacitance means we are inserting minus JXC. So if you have, this is XL, if you are inserting minus JXC, then effective denominator will be reduced and your power transfer capability will be improved. Now, as the amplitude of the post-fault power angle curve increases, the deaccelerating area also increases. Now let's have a look for this diagram. Let us consider that a finite machine which is supplying the power to the large grid through a double circuit line having 4 sections which are made possible by a midpoint bus. So if you see, these two are the 2 lines which are parallel to each other, and these are the 4 sections. This is suppose section 1, this is your section 2, this will be your section 3, let's say, and this will be your section 4. A fault in any of the section will increase the transfer reactance. Along with that, there will be reduction in the amplitude of the power angle curve. Now the faulty section will be isolated after a certain interval by simultaneous opening of the circuit breaker, and once the fault is clear, the amplitude of the power angle curve will be increased, that we know. Now the exertion of the power angle and the accelerating and deaccelerating area that we will discuss in the next slide with a P delta curve. Now let us consider a single machine which is connected to the infinite bus through a midpoint switching station. Here the circuit breaker S, this is the circuit breaker S, which is shunted by the capacitor C, and it is used in the switching station. Under normal condition, this switch S will remain closed and the capacitor does not come into the picture, which is shorted by S. But with the fault occurring on the same section at the same location, the fault power angle curve remains unchanged. However, the clearance of the fault will involve the simultaneous opening of the S and the line breakers in a sequence. Now as the S, that is the switch, opens, the capacitor C is in series with the 3 remaining sections, which will reduce the transfer reactance during post-fault condition as compared to that of when the capacitor and breakers were not in use, which is shown in the next P delta curve. So see, this is P delta curve. If you see this one is nothing but what? This is the curve for during fault situation. Then let's say this is the curve. First is the curve which is for pre-fault situation. Now here it has been shown post-fault with capacitor switch. This is your post-fault dotted line which is represented here with capacitor switch, and this line which is shown by arrow, it is post-fault without a switch capacitor. So if we haven't used any switch capacitor, what you will observe here? This will be your accelerating area. Let's say I will show it. This will be accelerating area. This will be a deaccelerating area. So it is observed that as A2 is less than A1, system will be unstable. System will be unstable. But when I connect this capacitor here, then what happens because of that? The effective reactance, as I discussed earlier, XL minus JXC, effective reactance will be reduced. As your effective reactance reduces, your power transfer capability will increase, or you can say the Pmax curve will increase. So that's why this increased Pmax curve, I can say, I will draw it here, dotted line, and I will show this is your Pmax. Now this is Pmax. When it will be? When we are connecting here series capacitor. Now if you take this much will be the area, this much will be the deaccelerating area, let's say up to this, suppose if you take. So what you observe here, by connecting the series capacitor, A2 will be greater than, or whatever will be equal to, it might be equal to, A2 is greater than A1, it is observed, so therefore system will be stable here. Now it can be seen from the deaccelerating area increases by the area of OABCDO, and therefore the stability of the system can be improved. Next one is nothing but by connecting the flywheel to the shaft of the rotor, the variation in the speed can be achieved. It slows down the velocity and therefore velocity of the rotor will decrease with respect to synchronously rotating axis. Now a flywheel is a heavy disc or a wheel that is attached to the rotating shaft. Flywheels are used for storage of kinetic energy. The momentum of the flywheel causes it not to change its position, that is rotational speed, easily, and because of this the flywheels will help to keep the shaft rotating at the same speed. Therefore, the transient stability can be improved here. This is due to the damping experienced by the flywheel. It absorbs the kinetic energy of the rotor. So this is a diagram. This is nothing but your shaft, and this is the flywheel which is connected to the rotor. Now the original swing equation considering the damping factor is m d omega upon dt plus d omega equal to Pa. Now this d is nothing but a damping factor. Whatever swing equation we derived earlier, there were a few assumptions, and one assumption was damping is neglected. So whatever derivation or whatever equation we got, m d square delta upon dt square equal to Pa. This is without considering the damping. So from this I can write like this also, d square delta upon dt square will be equal to what? Will be equal to Pa upon m. Now can I write this d square delta upon dt square as d omega by dt? Yes, because omega is the speed, d omega by dt you will get it as acceleration, d square delta by dt square is the acceleration, and we know that omega equal to what? D delta by dt. So if you substitute here omega equal to d delta by dt, you will get this only, d square delta upon dt square. Now if you see, the rotor acceleration can be represented from this equation whatever we have written. We can write d omega upon dt will be equal to what? Pa. This term I will shift, this total term I will shift here, so it will be minus d omega upon m. So by introducing the damping term, that is a d, or we can say damper winding in the alternator, the acceleration can be reduced, and once the acceleration reduces, the system will be near to the stability. Next is nothing but whenever the fault occurs, if the steam input is reduced, the accelerating power is reduced. Turbine governor will control the steam input to the turbine, thereby controlling the shaft input torque by opening or closing the steam valves. It reduces the acceleration of the machine. This can be achieved with the help of speed governing system. This topic is there in detail with automatic generation control, because we know that when the load is more, then we have to maintain the frequency also. We have to maintain the voltage requirement for that load. So for that case, we have to increase the steam inlet. So if the steam inlet is increased, then in that case what happens? More steam will be imposed on the blades of turbine, and turbine will rotate with a high speed, and again you will be able to maintain the frequency and the voltage. But here again, by reducing the steam, what we will basically do? We will basically reduce the speed of rotation of the blades of the turbine, and therefore in turn we can control accelerating power. Now by using automatic voltage regulator, we can increase the excitation. Here excitation increase means we will increase the PE. Now as we know that PA will be equal to PM minus PE. PM will be the constant, let's say. So, or it is a fixed value suppose. So more the PE, what will happen to the PA? PA will be reducing. So that's why PA will become negative. That is nothing but what? It will go into deaccelerating area. So therefore it reduces the acceleration of the machine. Now let's have a look for the next method which is used for improvement of transient stability. Reducing the reactance of the system by using larger air gap between stator and the rotor increases electrical output power PE, and hence it will lower the acceleration of the machine. So let's have a discussion about this. Let us say this is the rotor. Suppose if I have given here, let's say a DC supply plus minus. So I will draw this. This will be your one axis. You can say this is nothing but your XD. This will be your, let's say, XQ. Now we know that the air gap length we will represent this air gap length. It is nothing but, let's say, it is LG. So we know X equal to what? X equal to 2 into pi into F into L. But there is a formula of L also. L will be equal to L, or you can say self-inductance of an inductor, which is equal to what? N square divided by S, where N is nothing but number of turns and S is nothing but reluctance of the coil in ampere per Weber. So therefore I can write this as N square. Now for this S also we can write it like this. What is the formula? Lg divided by mu 0 into mu r into A, area. So how I can write this formula? L will be equal to N square mu 0 mu r into A upon Lg. So what we observe? Inductance L is inversely proportional to what? It is inversely proportional to your air gap length, that is, which is discussed here, air gap length Lg. So therefore now here what we have written, reducing the reactance of the system by using larger air gap means what? More the air gap, that is more will be the Lg, more will be the Lg. What will be your L? L will reduce. So I will write it here, L will reduce. As your L reduces, what will happen to your X? Your X is also going to reduce. X is also going to reduce. So you know that PE equal to what? It is EV upon X into sine delta. So reduction in the X, what it will happen? Increased in the electrical output power, that is PE. And again we know accelerating power PA will be equal to PM minus PE. So increase in the PE with compared to that of PM, what will you will get? You will get here answer as a negative, that is nothing but deceleration. So therefore reducing the reactance of the system, here you are reducing the reactance of the system L. How? By using larger air gap between stator and the rotor. Air gap is denoted by Lg. What it will do, or what it will create, it will increase electrical output power PE. Here you have seen electrical output power PE is increased, and therefore it will lower the acceleration of the machine. Next is nothing but fast acting breakers. Now whenever there is a fault in the system, voltage level will be reduced, that we know, and which results in a drastic reduction in the electrical power output PE. Because there is a fault, V will start decreasing, PE will be equal to what? It will be equal to EV upon X. So if E equal to 0, definitely your PE will be equal to 0. And if PE is 0 or it is lesser, we know that PA will be equal to what? PM minus PE. So if this is 0 or if it is less compared to that of PM, then it will prone to acceleration. This answer will be the positive. So as lesser the value of the PE, more will be the accelerating power PA. Now in the event of the sustained fault, the stability will get hampered. But whenever the fault is cleared, the electrical power output increases, in turn reducing the net acceleration power PA. The faster the clearance of the fault, the lesser will be the accelerating area, which enhances the stability limit. That also we discussed earlier. Let's say, suppose if I have this curve, I will draw this. Suppose this is my sudden increase in mechanical input. I will draw this. This is your area A1. This will be your area A1, and this is nothing but your area A. Now let's say this is my delta CR. This is my delta CR. Suppose if I try to draw this diagram again here, this is a curve. This will be your PM0, let's say. This is your increased in a mechanical input PM1. Now suppose, now this will be your first, and now if it is cleared, let's say at point, let's say this, what will happen? Here now the accelerating area will be more as compared to that of your deaccelerating area. So in that case, what you have to do, in that case, the whatever circuit breakers we have, it should be operated with a very fast. Then only the fault will be cleared, and once the fault is cleared, then your PE value will be regained to its original value, and in turn it will maintain your accelerating power PE. Now it is possible to have isolation of the fault by the speedy circuit breaker in less than 2 cycles. The lesser the time between the fault clearance instant and the recloser, the better will be the stability prospects. So this is also one way to improve a transient stability. Next is nothing but independent pole operation of the circuit breaker. Now the independent pole operation is nothing but it is a separate mechanism for each phase of the circuit breaker, so that the 3 phases are open and closed independent to each other. That doesn't mean suppose there is a fault on the one phase, then the circuit breakers of all the 3 phases should be operated. It should not be like that. If independent pole operation is there, then the failure of the one pole will not restrict the operation of the other 2 poles. Although the breaker poles operate independently of each other, the relaying system is normally arranged to trip all the 3 poles of any type of the fault. So with the circuit breaker designed for independent pole operation, a failure of all the 3 poles is highly improbable. If we use a 3-pole circuit breaker, then all the lines are isolated. In case of an line to ground fault on a single line, what happens? PE will be equal to 0, and as you know, PA will be equal to PA minus PE, PA will be more. But if we use independent or the single pole circuit breaker, then the supply can be maintained through other 2 lines. Wherever there will be fault, at that place the circuit breaker will trip, it's okay. But for other 2 lines, it will not be tripped, and electrical power will not be equal to 0, it will be non-zero. Yes, somewhat drastic change is there, or somewhat change is there in the value of PE, but it is not equal to 0. So therefore, due to this, the acceleration of the machine will be reduced and it improves the stability. You take a case, suppose if PA equal to PM minus PE, if this total equal to 0, then it is more positive. PA will be more positive. And if we take a case where this is not totally 0, some value will be there, then it is a positive, it's okay, it is positive, but it is not more positive as compared to that of your first case. The first case was the one where we are using dependent pole operation, and second case is the one we are using a single pole circuit breaker or independent pole operation. Thank you for watching this video. If you have any doubt, please feel free to ask. Thank you once again.